Assalamu alaikum, students. The topic of our today's lecture is wireless networks. Basically, we would be seeing two aspects of the wireless networks. Number one, the line of sight part, and number two, the cellular networks. And in both of these, we will try to calculate a few important design parameters, as well as we will analyze them accordingly. First of all, we'll see for all the wireless networks, one important component that we have to take care of, that we make use of, is an antenna. What is an antenna? An antenna is an electrical conductor or a system of conductors. In modern systems, we can have arrays of antennas or even two-dimensional arrays of antennas, which are used in modern communication, in which we can incorporate space domain multiple access, and the array, the steering arrays can be established from those. But that is part of array antennas, basically. But basically, in all the wireless communications, we do need antennas, and while for a communication that we undertake these days, this type of communication is basically two-directional communication or a full duplex communication. So we need to have a transmission as well as a reception antenna on both the sides. So what does the transmission antenna do? It radiates electromagnetic energy into space. And what does a reception antenna do? It collects the electromagnetic energy from the space. So the same antenna can be used for transmission and reception. Now let's see what are the radiation patterns. A radiation pattern is the graphical representation of radiation properties of an antenna. It is depicted in two dimensions, basically. And now the second part, second important parameter is the beam width when we are talking about an antenna. What is the beam width of an antenna? It is the measure of directivity of an antenna. Lesser the beam width, more the directive an antenna is. And how do we limit the width of a beam? By the half power. As we increase the angle on both the sides, the power reduces as compared to the central point. So when it reduces to half power on either side, we stop and we measure the angle. This angle gives us the beam width. Similarly, as the receiving antenna, there is an equivalent radiation pattern also, or the reception pattern also. Different types of antennas, like, let's see. The basic type or the idealized type of antenna is an isotropic antenna, which is basically a point antenna, a zero-dimensional antenna which radiates in all directions. Second important type of antennas is the dipole antenna. We can have half-wave dipole antennas, or the Hertz antennas, or the quarter-wave vertical antennas, or the Marconi antennas. And the one antenna that is used in abundance in telecommunication systems, especially for line of sight systems. That type of antenna is a parabolic reflective antenna. Basically, the antenna is like uh, we have a parabolic dish, and this dish is basically reflecting the electromagnetic waves, and it focuses on its focal point. And this at this focal point we have the actual antenna, and from this antenna there is a lead coming out of it, which goes down to the electronics that is placed on the ground. Now, what is antenna gain? The power output in a particular direction compared to that produced in any direction by a perfect omnidirectional antenna. Actually, it is the comparison of a particular antenna to an isotropic antenna, because the isotropic antenna does not have directivity, and all other practical antennas do have directivity, and that directivity accounts for the antenna gain. Another important parameter in antennas is the effective area, which is related to the physical size and shape of the antenna. Not only the size matters, which means that if we are using a radar and we are trying to locate an aeroplane, since the size of an Airbus or Boeing 737, it is quite large, it is quite easy to detect. But what happens when we try to detect a stealth bomber using a radar? The shape of the vehicle, or the shape of this particular aeroplane, is such that most of the electromagnetic waves that are sent by the radar are not able to be reflected back to the radar to be detected. Most of them are scattered, so it is very difficult to detect a stealth bomber, and that is due to the shape of that particular object. Now, what is antenna gain? It is a relationship between the antenna gain and the effective area. Let's see what is the relationship between the antenna gain and the effective area. G is equal to 4 pi AE over lambda square. AE is the effective area, and lambda, as you know, is the carrier wavelength. We can convert this formula in terms of F and C, and removing lambda, since F is equal C is equal to nu lambda, C is equal to F into lambda. So using that formula, we can also have F gain of the antenna equal to 4 pi F square into AE over C square. Now let's see what are different propagation modes. Historically, many different waves, frequency waves have been used, and each one has separate behavior. For example, we have three basic types. Number one is the ground wave propagation, and number two is the sky wave propagation, and number three is line of sight propagation. This is the ground wave propagation. If we have our frequency below 2 megahertz, then what happens that the transmitting antenna sends the signal, and the signal propagates, and it just moves along the surface of the earth, and it can reach farther distances. But this can only be done if we are using frequencies below 2 megahertz. So this is the first type of ground wave propagation. A famous example of this type of propagation is amplitude modulation radio, AM radio. What happens is that the ground wave follows the contour of the earth. It can propagate considerable distances. The second mode of propagation is the sky wave propagation. Actually, when we use the frequencies more than 2 megahertz and below 30 megahertz, what happens is that the wave does not move along the contour of the earth, rather it moves towards the sky, and from the ionosphere, which is above the atmosphere, it reflects back and comes to the earth. From the earth, it is again reflected back, and again it is reflected back from the ionosphere. In this way, very long distances can be achieved. So, two major examples of this type of communication is amateur radio and citizen band radio. Citizen band radios are normally used by truckers, the truck drivers, to communicate with each other. And the frequency that is used is between 2 megahertz and 30 megahertz. By the way, the remote control that is used for controlling small model aeroplanes also they use 27 megahertz. We can talk about that later also. The other example is the amateur radio. Amateur radio was an early version of chatting, in which voice chat was done, or some expressions were sent over long distances using skywave propagation, and you needed to have amateur radio license for that. But that era is almost gone, and maybe someone in Pakistan would still be using skywave propagation, but it is not that much popular now. Here is the distribution of the citizen band radio channels. We have different frequencies on which different channels are sent. We've got 40 different channels which use different frequencies. You can see the difference between them. 26.965 and 26.975. So this is the we have got this particular difference between these two frequencies, and in this way it uses the communication, voice communication is done over this. And these standards are basically defined by FCC, or the Federal Communication Commission, which is an equivalent of PTA in USA. FCC is the regulatory authority in USA. The third type of propagation is the line of sight propagation, in which there is a direct line of sight between the transmitter and the receiver, the transmitting antenna and the receiving antenna. Here in this interesting diagram, you can see that the earth bulge can also hamper in this type of propagation if the distance between these two antennas is increased quite further. If we keep on increasing the distance between the two antennas, a time would come when the line of sight would be a tangent to the Earth's surface. And as we go a little further, or as we go a little more to a more distant place to install our antenna, the propagation line of sight would be blocked by the Earth's bulge. The transmitting, and this is done after 30 megahertz, because at 30 megahertz the signal is not reflected by the ionosphere. That's why all the satellite communication is also done in this range. But satellite communication is not the only use of the line of sight communication. The terrestrial line of sight communication or the digital microwave communication that is basically done for terrestrial links, that also uses line of sight propagation. In line of sight propagation, the transmitting and the receiving antennas are within line of sight, each other's line of sight. But many things can be done, can happen to the signal. For example, refraction can happen, which is the bending of microwaves by the atmosphere, because the density of the atmosphere does not remain the same throughout as we go above the surface of the Earth. And in this way, the velocity of the electromagnetic wave that also varies, and it depends upon the density of the medium. Lighter the medium, the speed of the electromagnetic wave would be higher. But when the wave changes medium, the speed changes, and the wave bends at the boundary between the mediums. So that factor has also been taken into account for. Now, what is the line of sight? First of all, the formula that defines the line of sight, it basically depends upon the height of the antenna, while assuming that the curvature of the Earth's surface remains the same and the contour is smooth. In that case, the distance d, which is given in kilometers, is dependent only upon the height, or the square root of the height of the antenna. We multiply it with a number 3.57. In this way, we get a distance in kilometers, while the height is given in meters. If we are not, as we are not using actual light, and we are using some other frequency of an electromagnetic wave, and the actual line of sight is not the optical line of sight. It is actually the effective or the radio line of sight, which gives us a distance which is a bit farther as compared to the optical line of sight, because the signal goes beyond this optical line of sight, and this distance becomes 3.57 into under root k into h, where k is the adjustment factor and its value is 4/3. While keeping in view two antennas, with first of height h1 and the second of height h2, the maximum distance that can be achieved with these two heights is 3.57 into under root k into h1 plus under root k into h2, and that's all. Where h1 is height of the antenna 1 in meters, and h2 is the height of antenna, 2 in meters. Now, the line of sight wireless communication faces a lot of impairments also. First of all, the attenuation and the attenuation distortion. Attenuation means that as the signal moves along the atmosphere, it is attenuated. The power it contains reduces with the distance. And the second point is the attenuation distortion, which means that different frequencies get a different attenuation. So that is attenuation distortion. This is quite similar to the concept that we have already discussed for line communication also. Second, free space loss. What is a free space loss? What do you think if we do not have air in between and an antenna is radiating at a distance, for example, 10 meters, you get a certain value of power of the signal. If you go at 20 meters, would this value be reduced? Yes, it would be reduced, because as you move away from the source, the signal is distributed. It expands, and the actual receiver that is measuring the value of the signal, value of the power of the signal, its size remains the same, and smaller amount of power reaches it. The remaining one is distributed in a larger area. Then we've got noise. There are different types of noise that affect our line of sight communication. Then we have got atmospheric absorption. We have got our atmosphere has a particular characteristic of attenuation or absorption of electromagnetic waves. At certain particular frequencies, we have got peaks of absorption. So while using line of sight communication, we need to avoid those particular peaks. Since the air contains oxygen as well as water vapors, both of these elements, materials, have different absorption characteristics, and they have different absorption peaks. So both of their peaks must be avoided. And then we have got one more thing, which is multipath. Multipath is the reflection of our main signal from walls and floors and other things, and in this way, the signal that reaches our receiver, it is not a single signal. It is multiple signals reach the receiver at one time. So the receiver should be able to distinguish between all these signals, and it should be able to either superimpose all of these signals or select the most powerful ones to use for communication. Then we've got refraction, which is due to the difference of density of air at different heights. So this difference in density cause a refraction of the microwave signals. Then we've got thermal noise. Basically, thermal noise resides in the electronics of the communication links. That is the transmitter as well as the receiver. What is attenuation? As the signal moves along the distance between the transmitter and the receiver, its strength falls down. This is basically attenuation. The wireless media is also called the unguided media as compared to the guided media. For example, the optical fiber is a guided media. Coaxial cable is a guided medium because the signal remains in that particular cable or in that particular optical fiber, while in wireless case it is an unguided medium. So the received signal must have sufficient strength so that this receiver should be able to interpret the signal. If the receiver does not receive the signal of a certain strength, then it will not be able to assess what is sent. And the signal must maintain a level sufficiently higher than the noise to be received without error. This is especially important when we are talking about digital communication. The digital communication would be good if the signal to noise ratio is better, because if the signal to noise ratio is better, the bit error ratio would be very low. But if the signal to noise ratio is bad, is low, then the bit error ratio would be high, which is undesirable. Attenuation is greater at higher frequencies, causing distortion. Now, free space. What is free space loss? As I've told you, that as we move along the path, even if we are in free space, the signal basically expands. It does not move in a single line or a single very thin beam. Basically, it is not in a thin beam. It expands as it moves along. So as the distance is increased, the free space loss also increases by the square of the distance. So if we compare or find the ratio of the transmitted signal to the received signal, as you know, the received signal would always be of lower power unless there are many amplifiers or regenerators in between. So what would happen is PT, which is the transmitted power, divided by PR, which is the received power, would be equal to 4 pi d whole square divided by lambda square. And if we put it in the form of F and C, that is frequency and speed of light, it would be 4 pi f d whole square over c square. So it can also, if we want to put this particular formula in the form of dBs, it would be 10 log of PT over PR, which is 10 log of 4 pi d over lambda whole square. As you know how to deal with the logs of exponents, the exponent 2 comes down and multiplies by 10 and it becomes 20. So we have 20 log of 4 pi d over lambda. In this way we get minus 20 log of lambda, because lambda is in the denominator, plus 20 log of d plus 20 log of 4 pi, which comes out to be 21.98. You can calculate this on your calculators also. So, but if we convert it to F and C, it would become 20 log of 4 pi f t over c, and it would be 20 log of f plus 20 log of d minus 147.56. And what is 147.56? How did it come up? Actually, it is 20 log of 4 pi over 3 into 10 to the power 8. So we have the free space, and we have the gains of the transmitting and the receiving antennas, and we know the effective areas of the transmitting antenna and the receiving antenna. Actually, transmission and receiving is done on both the sides, so both the sides matter. That's why we can relate this particular formula in the form of 4 pi d whole square over g r into gt into lambda square, and it can also be written as lambda into d whole square divided by ar into at, or in the form of c and f, while avoiding lambda, we have c into d whole square over f square into ar into at. This can also be converted into the dB's form, and we get 20 log of lambda plus 20 log of d minus 10 log of at into ar, effective area of the transmitting antenna and effective area of the receiving antenna. And in the form of frequency and c, which is the speed of light, we can convert it to the form of minus 20 log of f plus 20 log of d minus 10 log of at into ar plus 169.58, and the answer comes out in dBs. Now, what are the different types of noise? First of all, we've got the thermal noise, as we have talked about. This is basically the electronic noise on the transmitter and the receiver side. Then we've got intermodulation noise, which is basically to do with the non-linearity of our systems, in which multiples of different frequencies are added up, and a lot of frequencies are generated. Thirdly, we've got crosstalk, which affects our communication, because if we have the effect of one communication on another communication, it would be called a crosstalk, and it is extremely undesirable in a communication system. Then we've got impulse noise. You'll see each one of them one by one also. Thermal noise is, as we said, it is due to the agitation of electrons, and it is present in all electronic devices and transmission. It cannot be eliminated unless we have all our systems or our electronics at 0 degrees Kelvin temperature. And it is particularly significant for satellite communication. So the systems that are designed for satellite communication, they need to take care of this particular noise in particular. To calculate the noise, if the bandwidth of the signal is 1 Hertz, then the thermal noise would be equal to K into T, where K is the Boltzmann's constant, which is 1.3 into 10 to the power minus 23 joules per degrees Kelvin, and T is given in uh, degrees Kelvin temperature, and N naught is the noise power uh, given in watts per 1 hertz. But if we have got a larger bandwidth B, then this value, this noise would become K into T into B, where and if we want to convert it into decibels, it would become 10 log of K plus 10 log of T plus 10 log of B. So this would be given in dBWs, and to get a dBW, it would become minus 228.6 dBW plus 10 log of T plus 10 log of B. The second type of noise is the intermodulation noise. Uh, if different frequencies share the same medium and the medium has has a behavior of non-linearity, it would cause multiple frequencies to add up. For example, 2 into f1 plus f2 and 2 into f1 minus f2, similar 2 into f2 plus plus f1 and 2 into f2 minus f1. Similarly, we can have 3 into f1 plus f2 and 3 into f1 minus f2. So many frequencies will be generated. Third type of noise was the crosstalk. It is the unwanted coupling between the signal paths, which causes overhearing somebody else's communication, and it is extremely not wanted, unwanted, undesirable in any communication system. Lastly, the fourth type of the noise is the impulse noise, which which is due to irregular pulses or noise spikes of short duration and relatively high amplitudes. These are caused by external electromagnetic disturbances or faults and flaws in communications. Now let's see what is EB over N naught. This is a very important value that is basically derived from uh, mm, uh, derived for the digital communication systems. So the ratio of the ratio of signal energy per bit. Here S over R means signal power per bit, and R is the rate in bits per second, whole divided by N naught. N naught is the noise power. So it becomes S over KTR, right? So R is like, if here we are considering that R is equal to B, which means that 1 hertz is equal to 1 bit per second here, since R was taken in bits per second. The bit rate of the signal of a digital function is a function of the bit error rate, or the BER is basically the function of EB over N naught. Actually, on the base of it, it is signal to noise ratio, and normally in our formulas that we use in communication systems, we use EB over N naught. As the bit rate R increases, the transmitted signal power must increase to maintain the required EB over N naught, which means that if uh, if the data rate that we want to transmit from one point to the other is small, then smaller power or smaller EB over N naught would suffice. But if the data rate increases, then we need to increase the EB over N naught ratio. and that can only be increased by increasing the transmitted signal power, because N naught, or the noise, remains the same normally. Other impairments that a communication over wireless would face are the atmospheric absorption, which is due to the water vapors and oxygen. I've already talked about it, that the water vapors and oxygen have their own separate characteristics of absorption of electromagnetic power, and it varies with the frequency, and both of these exhibit spikes at certain frequencies also. So while we are using some communication system or engaging in a communication system, we must avoid those spikes of absorption. So because that would hamper our communication drastically. So what is multipath? This is another type of problem that we have to face. From the obstacles, the signal reflects and many copies of the same signal with different delays, they come to the receiver. Now it is up to the receiver to either to add them up by giving intentional delays to the early coming signals and adding them up, all up, or the other thing that can be done is that it can um, select the most powerful signals and reject the weaker signals. Normally in 2G systems that is done, but in 3G systems the rake receiver is used, in which what it does is that it receives the signal copies with different delays and different powers, and it not only gives delay to the earlier coming signals accordingly, so that all are synchronized and they are added up, and a superimposed signal is presented to the receiver. Another important uh, factor of impairment in wireless communication is the refraction, or the bending of radio waves as they propagate through the atmosphere. Because the atmosphere is denser uh, in the lower heights, and it goes on and keeps on thinning as we move upward. Here in this diagram you can see an example of multipath. Basically, signals are coming to this car directly, not directly. Here it is coming through scattering, through reflection, through diffraction. So there are three methods of coming of the signal coming to this uh, particular car. So multipath propagation uh, has three sources. Number one, reflection. Number two, diffraction, which occurs at the edge of an impenetrable body that is large compared to the wavelength of the radio wave, and the scattering also. And what are the effects of multipath? Number one, the multiple copies of signals may arrive at different phases. If the phases add destructively, the signal level relative to the noise declines, making this detection difficult. While it can also we can also face intersymbol interference. One or more delayed copies of the pulse may arrive at the same time as the primary pulse for a subsequent bit. So different types of fading that are faced in wireless communication are the fast fading, which changes as the receiver changes its position by a very small distance. Then there is slow fading. Then there is flat fading. Then there is selective fading. Then relay fading and Riccian fading. The errors can also be compensated, and there are many methods defined by engineers to do that. First of all, the major method is forward error correction. Then we've got adaptive equalization. Then diversity techniques are used. In the forward error correction, what happens? The transmitter adds error correcting codes to the data block, and the receiver calculates the error correcting codes and identifies the position of the error, and either it corrects it, or if it cannot, then it can ask for a retransmission. Then we've got an adaptive equalization method. It can be applied to transmissions that carry analog or digital information, and it can be used to combat inter-symbol interference also, and it involves gathering dispersed symbol energy back into its original time interval. So there are two basic and accepted methods of adaptive equalization, including the lumped analog circuits and sophisticated digital signal processing algorithms that use adaptive equalization. Then we've got diversity techniques. Basically, individual channels experience independent fading events. So we use more than one methods of sending the signal, or more than one channels of sending the signal for sending the signal. For example, space diversity, it involves physical transmission path. Then frequency diversity, in which the signal is spread out over a large frequency bandwidth or carried on multiple frequency carriers. And CDMA and direct sequence direct DSSS, direct sequence spread spectrum method, which is used in 3G systems, and the frequency hopping, that is also another example of the frequency diversity. Then for time diversity, the data is spread out over time, over different time slots, for example. Now, what is the Fresnel zone? When we have a line of sight communication, that does not mean that the communication path consists of a very thin line that connects the two antennas. Basically, as we move along the path from the transmitter to the receiver, it expands. The signal expands, and similar is the system on the other side, signal on the other side. So in the center we have got a large radius, which is called the Fresnel radius, for which in this Fresnel radius we should avoid having any interfering object. For example, in between the transmitter and the receiver, we have a building or a tree or minaret. It would hamper the communication very badly. So to find out the value of of the radius of the first Fresnel zone, the formula is R is equal to under root lambda SD over S plus D, where lambda, as you know, is the wavelength, and S is the distance from the transmitter to the to the highest point in between, and D is the distance from the receiver to the highest point in between. If the whole route is plane and the contour is as of a normal circle, then both of these S and D would be equal. Now, what is atmospheric absorption? Above 10 gigahertz, molecular absorption takes place. For example, the peak of the water vapor absorption is 22 gigahertz. Peak of oxygen absorption is near 60 gigahertz. So we need to avoid these two particular frequencies. So the favorable windows for communication are 28 gigahertz to 42 gigahertz, and from 75 gigahertz to 95 gigahertz. In this way, both of these frequencies, which are the peaks, absorption peaks, they are avoided. Now there is also a great effect of rain on the attenuation also, and it depends upon the rate of the rain in millimeters per hour, as well as uh, the drop size. So the attenuation in dBs per kilometer is A into R raised to power B, where A and B depend upon the drop size and the frequency. There is also a great effect of vegetation on our communication over line of sight. As we have already seen and calculated the Fresnel zone, uh, what we need to do is to avoid any obstruction within the 60% of the Fresnel zone. First of all, we need to take care of the height of uh, the earth bulge that comes in between. That determines if there is no uh, uh, vegetation on it and the whole earth between the transmitter and receiver antenna has a normal curvature. What happens is that um, uh, uh, we only need to take care of the earth bulge. As we move away from, as both the uh, antennas, transmitter and the receiver antennas, move away from each other, the the earth bulge comes closer to the center point of or the line of sight, basically. And if it enters into the 60% of the Fresnel zone, the communication is hampered drastically. Now let's see what are the cellular networks. Cellular network organizations normally use multiple low power transmitters, 100 watts or less. They make cells of hexagonal shape, which fix into each other like beehive. You can see the beehive cells. It is almost like the beehive cells. Each cell has its own antenna and is served by a base station, which consists of transmitter, receiver, and control unit. A certain band of frequencies is allocated as far as 1G is concerned. cells set up such that antennas of all neighbors are equidistant, and that can also be only be possible in a hexagonal pattern. In these two diagrams, you can see that if we had square patterns, the distance between the center of different cells would not be equal. The differences between four cells which are above, below, on the right and on the left, those would be equal, but diagonally that would be a different distance. We need to have those distances equal so that that would help in calculating the value of the power that is transmitted, and it would later on help us in handoffs. In the hexagonal pattern, you can see that we have radius r of each cell and a distance d, which is the distance between the centers of the equidistant centers of the adjacent cells. This is termed as small d. Another term would come up later, which is capital D, which is the distance between the centers of co-channel cells. That is, the channels that use the same set of frequencies. Since the frequency that has been issued by the mobile company is limited, so the the cellular company would like to reuse that that frequency set um, uh, again and again. But we need to maintain certain distance between them. So adjacent cells are assigned different frequencies to avoid interference or crosstalk. The objective is to reuse frequency in nearby cells. 10 to 50 frequencies are assigned to each cell. Transmitted power is controlled to limit the power at that frequency escaping to the adjacent cell. So the adjacent cell does not uh, face crosstalk in case of FDMA, and in case of 3G, it would face basically increase in the uh, height of the noise floor. Now the problem is to determine how many cells must intervene between the two cells using the same frequencies, which means that how much distance in terms of cells should be introduced in between two cells which use the same frequency sets. Here we have free frequency reuse patterns with different reuse factors. If the reuse factor n is 4, then it also means that we have 4 sets of frequencies allocated, which are used in such a way that if, as you can see in diagram A, figure A, you can see that a cell which uses a frequency set 1, that is in the center, and all the cells that are in direct neighborhood to it, they do not, none of them uses the first set of frequencies. They use 2, 3, 4, 2, 3, 4. It means that they use the second set, the third set, the fourth set, and even in this particular pattern also, near the cell which uses the second set, where it is written 2 in the cell, you cannot see another 2 in direct connection to it. After one neighborhood, it would be you would see another 2. Similarly, after one neighborhood, you will see another 1 in the central 1 case. This is the case for n is equal to 4. Now let's see what is the case for n is equal to 7. If we have got 7 different frequency sets, and the first set is given to the central cell as shown in the figure, you can see that the cells in direct neighborhood to the cell using the first frequency set, it does not contain a 1. The second neighborhood, 5 6 7 5 6 5 7 6 2 7 3 2 4 3, that also does not contain a 1. But farther than that, you can find a 1 more than 1 times. So we've got a distance of at least 2 cells from the cells from between the 2 cells which are using the same frequencies, and that is the case for n is equal to 7, or the frequency reuse factor equal to 7. In C part, you can see a frequency reuse factor of 19. In this case, you can see that you don't have the same frequency in next 4 neighborhoods. In the 5th neighborhood, you get the value, the same frequency, which is shown by the darkened cells. As an example, we take an example of an FDMA or an AMPS system, 1G system, where K is the total number of frequencies allocated. Capital N is the number of cells in the system. If the pattern consists of n cells and each cell is assigned the same number of frequencies, then each cell can have K divided by n frequencies. For amps, K is equal to 395, which is the total number of frequencies. Taking n is equal to 7, the smallest pattern that can provide sufficient isolation between 2 users, that is at least 2 neighborhoods. In the 3rd neighborhood, the same frequency would be reused. So there would be 57 frequencies per cell on average. Now, what is capital D? Capital D is the minimum distance between centers of cells that use the same band of frequencies, or the co-channel cells. Capital R is the radius of the cell as defined earlier. Small d is the distance between the centers of the adjacent cells, and small d is also equal to under root 3 into R. We got this value using geometrical calculations, since we are using hexagonal patterns. Capital N is the number of cells in repetitious pattern. For example, in the earlier example, we used n is equal to 7. It is also called the reuse factor. In a hexagonal cell pattern, only the following values of n are possible. N is equal to I squared plus j squared plus I into j. So I and j values can only be 0, 1, 2, 3. While I and j can have values 0, 1, 2, 3, or all the whole numbers. So the values of n would be 1, 3, 4, 7, 9, 12. So the relationship would be d over r is equal to under root 3n. But as the capacity requirement increases, which means that more and more users come in, how do we cope with that? Number one, what we can do is that we can add new channels. Number two, what we can do is that we can borrow frequency from the adjacent cell. If your cell is congested and the adjacent cell is not, then we can do is we can split the cells, and the areas of high usage can be split into smaller cells, for example. Then we can use different sectors separately, so we get wedge-shaped sectors with each with its own set of frequencies. That design can also be done. And after all, we can have microcells, which means that antennas uh, are within a building on the lamppost, which means uh, a, a large number of small antennas are used. Here is a diagram showing the cell splitting method or methodology. Thank you very much.